Hi there and welcome to our next edition of our C5 chemistry topic on how much quantitative analysis, and in this lesson we're going to be looking at the contact process. So here are our objectives for this lesson. Okay, so the contact process objectives are, by the end of this lesson you should know and understand how sulfuric acid is produced on an industrial scale. So we're going to look at the reactions and the physical method of actually carrying out the reactions to do it. Okay, so the contact process is used to make sulfuric acid. So if we have a quick look at the formula of sulfuric acid, then we can then go through the steps to see how it's actually made. Now, sulfuric acid has 2 atoms of hydrogen, 1 of sulfur and 4 of oxygen. Now we can actually split this into 2 down there. Now what this gives us is it gives us H plus, and there's 2 of those, and here we've got an SO4 2 minus ions. So we've got 2 ions, 2 H plus ions and 1 SO4 2 minus ion. Now sulfuric acid is got a variety of uses. It can be used for making medicines, it can be used for paint, as well as a raw material for many other chemical processes and pathways. Now the first stage of the contact process is to make the sulfur dioxide from sulfur. Now we'll see this all the way through where we've got the 3 stages for it, and today, or for this stage, we're looking at the first one, which occurs in the furnace. So what happens in the furnace is we have 2 raw materials, which are sulfur and oxygen, react to give sulfur dioxide. Now this is not an equilibrium, it's a straightforward forward reaction that enables sulfur dioxide to be produced. Now if we have a look at the stage 2 reaction, now the sulfur dioxide comes from the stage 1 process into the reactor, and again we have more air being given in, and we also have a catalyst here at the bottom. Now if we now have a look at the reaction that we've got, okay, now unfortunately I haven't got the arrows to be able to draw the equilibrium arrow, which should look like this. Sadly I've just got the 2 ordinary arrows, but that's what they should look like. Now right. Now what happens is we've got a couple of conditions that we need to be aware of. Now the reaction has obviously an endothermic and an exothermic direction. Now the exothermic direction is the forward reaction. So that is the exothermic, and then this is the endothermic. Now the conditions that this reaction is in is at 450 degrees C. Now this will favour the backwards reaction. Okay, so it would mean that the sulfur trioxide would break down. Now it's more of a compromise to have the temperature at 450 degrees because you get more of the collisions between the sulfur dioxide and the oxygen. So rather than having it really high, which would obviously favour this, or really low that would favour this, it's a compromise in the middle. Now as we saw in the diagram, there is a catalyst. Now the catalyst is vanadium pentoxide, which has this formula here, V2O5. Now this again doesn't favour either the backwards or the forwards reaction, it just speeds up that reaction. So this reaction is sped up and so is this one. So it means that if you're removing some of this, then you are going to get more of the reaction. Now again, if we remember back to the lesson on equilibrium, we looked at the favour or increasing the pressure or decreasing the pressure, how that would favour. Now here on this side we've got SO2, which is a gas molecule, and we've got O2, which is a gas molecule. So on this side of the equilibrium we have two molecules of gas, whereas on this side, the sulfur trioxide, there is just the one. So Le Chatelet's principle says that a higher pressure would favour the equilibrium direction with the fewer gas molecules, so we would favour the right hand side. So to do this second reaction we do need a fairly high pressure. However, there is one thing that we need to consider, and that is the cost. If we want to have it really high pressure, it's going to cost a lot of money to actually facilitate that high pressure. So you want it high pressure without making sure that the cost is too high. Okay, so stage 3 happens as the last stage, and this is where we actually produce the sulfuric acid. So we can see that the sulfur trioxide made at stage 2 is then reacted with water, which is our next raw ingredient, and then we end up with our sulfuric acid. So if we have a look at our diagram again, we can see here that the water is added to the absorber. The sulfur trioxide made from stage 2 is added, and we end up with that reaction. Now the sulfuric acid can then be taken off and it can be used, sold for any of the purposes that we said before. Medicine production, chemical production for medicines. It can be just used as a normal lab reagent as well.
Okay, so what we have done today is we've looked at the contact process where we produce sulfuric acid. We've looked at the 3 different stages where we make sulfur dioxide, the equilibrium that makes sulfur trioxide, and then the final reaction where we end up with our finished mixture of water with the sulfur trioxide to make sulfuric acid. Just remember about the conditions that we need, and I will see you next time. Take care. Bye.